Okay, in this vignette we're going to be discussing Nernst equilibrium and Nernst. These are the objectives you need to learn from this video. You can put your computer on pause and then write it down. So first of all, what is Nernst? Let's do some background work, then we'll get to a definition of what Nernst actually is. If you have a membrane, an ion, doesn't matter which one it is allowed to flow through here, you'll have a flow. Whenever you have a flow, you'll have a current. An electrical current is like the wiring in your house. And we measure current as voltage. Now, in the case of human physiology, we're looking at millivolts, not volts. So the correlation is, very simply, if the flow increases, the current will increase and the voltage will increase. If you make this a little smaller and the flow decreases, then the current will decrease and then the voltage will likewise decrease. The voltage is directly related to the amount of flow. The faster the flow, higher the voltage. The slower the flow, the lower the voltage. So if you have maximum voltage, you have to have maximum flow. One thing which is required for Nernst to be reached is unrestricted flow. If it is unrestricted flow, it'll flow through as fast as it can and just get the highest voltage it can. If you start restricting the flow by making this hole smaller, for example, this gate smaller, the voltage will decrease. So the correlation is the faster the flow, the more the voltage, the slower the flow, the less the voltage. And to have maximum flow, you have to have unrestricted flow to get the maximum voltage. Now let's continue on with the Nernst. Here's the membrane, ions on one side, that's on the other side. According to the law of diffusion, these ions are going to go from high concentration to low concentration. It doesn't matter what the ion is right now. And due to diffusion, due to the concentration gradient, these will start flowing through the gate into the side. What you see happening, so you have a movement this way based on the concentration gradient. But as it does so, remember your ions have negative ions in the interstitial fluid, not just positives. As you have the concentration gradient pushing it, in this case, pulling the chemical this way, you have an electrical gradient trying to pull it back because opposite charges attract. So you have concentration pushing it this way, but the electrical side is trying to make it go back this way. So at one point in time, the push for diffusion is going to equal the pull for the electrical gradient, and that level is called the Nernst equilibrium. Each of the major ions has their own voltage for this. Now again, for this to occur, they have to flow by diffusion. That flow must be unrestricted. If you restrict the flow here, you won't have the full speed of diffusion, you won't have this forever reached. So this flow has to be unrestricted, just as we discussed earlier, for this to occur. Let's do some drawings. from our voltage chart. The large N with the small I on the letter is the format for Nernst. So you have Nernst for potassium and Nernst for sodium. And it'll start at 0 voltage here. You have more concentration of potassium inside the cell than you do outside. So if you allow potassium to flow out of the cell, unrestricted flow, the voltage which it will achieve will be negative 90 millivolts. So if a reach had no voltage across its membrane, measuring inside from the outside, if there's no flow, there'd be no voltage, you'd be at 0 volts. If it lets potassium leave unrestricted flow as fast as it could, the voltage across its membrane will be negative 90 millivolts. Okay, let's go back and bring it to 0 again. If we're at 0 volts, and we'll just stop this, don't pay attention to that now. And let's look at sodium. Have sodium, if it were allowed to come into the cell, because you have more sodium on the outside than you do inside, the osmosis of the diffusion be towards the side of the cell. If we're for it to flow into the cell as fast as possible, unrestricted flow, the voltage it would reach would be plus 60 millivolts. If you were to restrict the flow of sodium, you wouldn't reach plus 60. We only get, let's say, plus 50 or plus 40. So you have to have unrestricted flow to reach the Nernst equilibrium for sodium of 60. Excuse me, same here. If you have unrestricted flow, the voltage reach would be negative 90 millivolts. If you reduce that flow, it wouldn't get to negative 90. It may only get to less than negative 70, for example. So to get these Nernst numbers, negative 90 for potassium, plus 60 millivolts for sodium, you must have unrestricted flow of those ions in the membrane. So we describe the Nernst equilibrium as the equilibrium between the diffusion of ions across the membrane with a chemical gradient in opposition to the electrical gradient. The Nernst for sodium is plus 60 millivolts. Nernst for potassium is negative 90 millivolts. What's required for Nernst to be reached? You must have unrestricted flow for this to be reached. If you restrict this flow, you will not get that. So you must have unrestricted flow. An effective optimum flow of ions, if you open this, let's say you're set at, it's not open, it's not unrestricted, it's open somewhat, unless your voltage is at plus 30 millivolts. If you open up larger, let more flow in, it's going to start going towards plus 60. Okay, that's your Nernst equilibrium.